must determine the principal that must be invested today to have a known amount in the future, so present value. Eric's parents plan to invest some money so that they can buy a car for their son in 5 years. That's nice of them. They estimate that 5 years from now, they will need $10,000 to buy a good used car. One bank offers 6% interest compounded annually. That's pretty good. They're not going to turn that down. Which of the variables in the compound interest formula are known? All right. Well, we know the amount that they want to have, $10,000. We know the interest rate, 6%, and we know the amount of time that they would like to leave this invested. It's going to be 5 years. The only thing we don't know here is the principal. So what can we do? We can substitute the known information and simplify. That's one way that we could solve for p. The other way that we can solve for p, which is what we're going to get to, is to simply rearrange this formula to begin with and have p on the left by itself and the rest of it on the outside. But we won't be using p and a. We'll be using pv for present value and fv for future value. So let's finish off our example here with the things that we know. We know the amount that they want, 10,000. We don't know p. We know the interest rate as a percent, as a decimal, is 0.06, and we know the exponent n is 5 for the time in years, 5 years. And go ahead and solve for p. Well, to solve for p, I really just have to divide both sides by this whole bracket. So I'm going to get that p equals 10,000 over 1.06, adding up inside my group here, to the power of 5. All right, chuck that in your calculator, click, 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 and we come up with a value of $7,472.58, rounded to the nearest cent. So what does that tell us? It tells us that the principal that needs to be in that account that his parents open, if they want to have $10,000 in 5 years, they need to put in almost $7,500 today in order to buy Eric a safe, reliable, used vehicle. All right, on the rest of that page, in the middle there, you have some space for notes. I'm going to be doing some formula work on the left and then some written notes on the right. When the principal P needed to generate a known future amount is unknown, so when we know the future amount but we don't know the principal investment, the compound interest formula can be rearranged to isolate P. So here's our compound interest formula, and now we're going to simply rearrange to solve for P, and I'm going to also swap sides here. So I got P on the left, and I'm going to divide both sides by 1 plus I to the power of n. And there we have our present value, future value formula. Okay, so what we're going to do is we're actually going to swap out P for PV, and the amount, we're going to use FV for future value, and the denominator remains the same. Okay, so we would write where I is the interest rate as a decimal, comma, per compound period, per compounding period, and n is the number of compounding periods. All right, so there's our formula for present value. You can also use it for future value. Future value would just use it in this this form. Okay, off to the right. Couple of notes, present value. What is it? This is the principal invested or borrowed. So our example so far, we've talked about investing in order to earn money. Same principle applies to borrowing money. So how much money you would borrow today, and the future value would be how much you then owe if you're going to pay it back all in a lump sum. That's not traditionally how we do it, but again, this is a stepping stone to understanding. We typically pay things back periodically or at regular intervals, but we learn about that a little bit later. So present value, the principal invested or borrowed today to result in a known future amount. And we would also then need to know the interest and the time conditions. All right. Next definition. Future value. Future value. This is the amount that a principal invested or borrowed will grow to. And again, we need to know the interest and the time conditions for these things. But you can work both ways. You can work from a present value to a future value, or you can work from a future value back to the needed present value. Example number 1. Calculate the present value. Sahar wants to invest money today in order to have $1,000 in 6 years. If she invests her money at 5.75% per year, compounded quarterly, how much does she need to invest? So, step 1. Step 1, identify given information. So what do we have? What are we working with? And that will allow us to apply our formula. We know the future value, right? That's the amount that she wants to have, $1,000. We know the interest rate, but be careful, I stands for the interest rate per compounding period. We're given 5.75% per year. So we need to do two things here. We need to first convert 5.75 into a decimal, which looks like that. And then we need to divide it by 4 because it's being compounded quarterly. So there will be 4 compounding periods per year. So we take the rate per year, divide it by 4. That will give us the interest rate per compounding period, which is 0.014375. And we want to keep a whole bunch of these decimals because we don't want to lose information. We don't want to round too early. If you start taking this amount, right, this goes in our formula and it's raised to an exponent. So this amount, this value, is going to get multiplied by itself, all of these decimal places, multiple times. And every single time it gets multiplied by itself, depending on the value of n, you would be losing information. You would be rounding further and further from the truth. So we want to keep all those decimal places, at least for now, and we round at the end. The other thing we know about this situation already is n. We're told that it's going to, and n stands for the number of compound periods. So we have 4 per year, and we're going to do this for 6 years. So n equals 24. All right, very common mistake in these applying this formula would be to just plug in the 0.0575 as I and plug in 6 as n and go for it. Okay, it's not the same thing. You'll get an answer that's fairly close, But again, the more compounding periods, the faster this investment is going to grow. So we want to make sure that we're doing it properly. Well, here we go. Step 2. Sub information into formula. Sub the information into the formula. So we're trying to determine the present value. So we're going to use our formula as PV equals FV over 1 plus I, close bracket, to the power of n. Sub in what we know on the right here. We know the future value, 1,000. We know I is 0.014375, close bracket, and to the power of n, which is 24. A little bit of carefully clicking away on our calculator. We can reduce this. We'll leave the numerator, reduce the denominator. I'm just going to put this together, right? This group is now 1.014375 to the power of 24, which equals approximately 709.96. So now we're going to round to 2 decimal places because we're talking about money. What does this tell us? Sahar must invest $709.96. Why? To have $1,000 in 6 years. Okay, the amount that we want, the future value was known, the 6 years was known, the interest rate was known, and we simply use our formula to figure out the present value. That is the amount that Sahar must invest. Okay. In example 2, we're asked to determine the number of compounding periods. So our dear friend Tamara received $250 for her 14th birthday, which she invested at 6% per year. Then on Tamara's 18th birthday, her investment is worth $317.62. How frequently was the interest compounded? So again, let's say, what do we know? Step 1, known. What do we know? We know the present value. We know the amount that she invested in the first place. It was $250. We also know, in this case, the future value. So we're not using it to find the present value. We're not using the formula to find the future value. That's $317.62. Now we are going to put a line for I and a line for N. Now we remember what these things are. The interest rate is the interest rate per compound period. And the question is, how frequently was the interest compounded? So we're not given the compound period, but we are given the annual rate. So the interest rate here is in the numerator, the annual rate as a decimal. And in the denominator, we need to divide that by the number of compound periods per year. We don't know that. So I'm going to use the variable x to represent the number of compounding periods per year. I'll make a note of that after, but we need that same x in the number of compound periods. Okay, so we know she's going to do this for 4 years, from 14th birthday to 18th birthday, but we don't know how many times it's going to happen per year. Okay, so a little note that we're going to do here for the I and the N. We're going to let x be the number of compound periods per year. Okay, so again, we took our annual rate and we divide it by the number of compound periods per year, which we don't know. And we take n, that's the number of compound periods per year, times 4 years. All right, now we can, step 2, sub in. So we take our formula, PV equals numerator of FV, future value, over 1 plus I, close bracket, to the power of n. We sub in what we know. We know the present value, 250. We know the future value, $317.62. 1 plus I. I is 0.06 to the power of x, and our exponent of n is 4x. Now this is where it gets a little bit tricky. We can't solve for this using standard algebraic techniques. Okay, we don't have the skills to do this pen and paper. So instead, we're going to solve for it graphically, which basically just means we're going to graph both sides of the equation and see where they intersect. Now, comma, graph both sides of the equation to see where they intersect. All right, so we're going to head over to Desmos. We're going to graph the left side, y equals 250, and we're going to graph the right side, y equals this whole chunk. And you're going to get a line that looks like this, and you're going to get a line that looks like this, and eventually they're going to meet. And where they meet, that's where they're equal. So where they meet, we'll know exactly the value of x, which is the number of compound periods per year. Let's go ahead and do that. Okay, here we are in Desmos. And all I have to do, again, is type in y equals 250. That's the left side of my equation. And the right side is a little bit trickier to type in, but we do it very carefully as we go here. The numerator is 317.62. I'm going to divide that by a large group here. In the group, I'm going to have to use a double bracket because I have 1 plus, I'm going to put this in brackets, 0.06 divided by x, close bracket, to the power of, I want to have that whole thing actually in that group, to the power of 4x. And let's see, that's about right. Let's see what we drew here. We're going to change our scale. All right, so I've changed my scale so that I can see this blue rational function, and I have a linear function here at y equals 250. And I'm just going to change my scale so that I can zoom in on that line and kind of see more accurately where these guys meet. So from my y-axis, I don't want to see much of anything except for that line. So I'm going to go from 245 to 255. And then I'm just going to follow that line and see where they meet. And Desmos is really great, somewhere in between 12 and 14 here. Oh, there we go. So it automatically zoomed in on that line. I'm now at the point of intersection. They're intersecting there. I can see the value of 250 at an x value of 11.857. So I'm going to just jot that down, that they intersect at, I'm going to round up to 12. X value of 12, a y value of 250, which gives us an x value of 12. Well, what was x? X is the number of compound periods per year. That makes sense. It's compounding monthly, right? Interest is compounded 12 times per year, or monthly. And there we have it. So it was a bit too tricky to do by hand, We simply go over to Desmos, we graph both sides of the equation, we find out where they're equal, that's where they intersect. They intersected at an x value of 12. X represents, in this case, let x be the number of compound periods per year, so 12 times, that's monthly. Okay, there is a second way to do this, not using Desmos. There are things online called a Tvm Solver, which basically will allow us to put in our known values. It's a special calculator that allows us to put in our known values, and it will pop out the missing value. So we're going to go ahead and do that now as well. Okay, so I'm here in the Tvm Solver. I just Googled Tvm Solver and clicked the first one that came up. This one's from GeoGebra. And I'm going to punch in what we know. So N is the number of years that investment is happening for. It's going to be for 4 years. I is the interest rate. In this case, it's as a percent. So I just put in our 6%. I'm going to leave present value blank, even though we know it's 250. I'll explain the reason in a second. Payment, we're not making any extra payments on this thing, so that's 0. We know the future value is $317.62. Payments per year, we're not making any payments, so that's unimportant. It's not going to get calculated. And then compound periods per year, we're going to have to use trial and error here. We already know it's 12 because we did it graphically. But if you didn't know that, you'd have to use guess and check. And basically what we're going to do is we're going to say, okay, here's all our information. And we're going to do it 1 compound period per year. We're going to solve for present value. Now, if we got 250, we would know that we were right on. Okay, it turns out that in order to come out with the future value that we intended, we would have needed to invest a little bit more than $250 if it was only going to compound once per year. So in order to make this amount less, that is to make your starting amount less to grow to the same final amount, future value, we're going to need to compound this more often. So why don't we try quarterly, see what happens. Hit solve for present value again, and you see it went down closer to 250. We're still not there yet though, okay? Well, what if we tried daily? What if we compounded this thing 365 times in a year? Well, now I'm a bit lower than 250, so that didn't work. So let's try monthly. Solve, and we get $250 right on. So this tells me that in 4 years at 6%, I can take $250. Compounding monthly, it will turn into $317.62. That's how to use a Tvm solver. You can use it for any missing variable, okay? Particularly helpful when we're solving for N or for compound periods per year. Again, this one was GeoGebra. I'm sure you Google it, and they're all very similar. Play around with it, see if you can get it to work. That's how we used systematic trial or guess and check to figure out that there were 12 compound periods per year. Example 3, applying this to help us choose the best loan for borrowing money. So Lamar wants to borrow some money now to buy a motorcycle and some riding gear. He estimates that in 5 years, he'll be able to pay back the amount of $12,000. So he's going to be able to pay back $12,000 in 5 years. So he's wondering how nice of a bike and gear he can afford today and what his loan is going to be on that. So we have 2 loan options, and we're figuring out which one he should choose and why. We are going to just take down our important information. He's going to pay back $12,000 in 5 years. So it's, again, this is not, he's not paying in increments like over 5 years, $100 at a time or $500 at a time or something like that. He's going to pay it all back in a lump sum after 5 years. So you can see how this isn't that practical, but it's a step in figuring out how to do this. That's why in the Tvm solver you have payments per year as well. That's traditionally how you would do it, like for a mortgage or for a car loan, you'd pay back monthly. Anyway, here we go. Payback. Lamar is going to pay back $12,000 in 5 years. He's got 2 options. He's got Regal Bank, RB, which is going to be, they charge 8.9% interest semi-annually. And then we have Suburbia Credit Union, SCU. They are going to charge 8.4%, so less interest, but it's going to compound monthly. So we're going to see the power of compounding periods here a little bit. All right, it seems like this one's lower, but it's compounded more often. So let's use our formulas to figure out which bank Lamar should go with. So we've got RB over here, and we've got SCU off to the right. We're going to take our future value formula. We're just going to take what we know for now. We know that he's got $12,000 being paid back in 5 years. That's the future value. So that's as big as his loan is allowed to get over the 5 years, okay? We've got an interest rate over here as a decimal of 0.089. We're going to divide that by our compound periods per year. Semi-annually means there's 2 compound periods per year, which gives us an interest rate per compounding period as 0.0445. And the number of compound periods for 5 years, 2 compound periods per year. That's an N value of 10. Let's go over to Suburbia Credit Union. Again, future value, 12,000. The loan can't grow greater than 12,000. We take our annual interest rate, which is 0.084. We're going to divide it by 12 because it's compounding monthly. That gives us a value of 0.007. That's the interest rate per compound period. How many compound periods? 5 years times 12 compound periods per year gives us 60 compound periods. Okay, let's sub that into the present value formulas. All right, so we have on the left here for Regal Bank, present value equals in the numerator 12,000, in the denominator 1 plus 0.0445 to the power of 10. Trusty calculator, click, 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 click. 7764.2, and because it's money, 20. This tells us that he can afford to spend $7,700-ish on his bike and his gear. Let's go over to Suburbia Credit Union. Present value, that's how much he's allowed to spend right now, is equal to 12,000 over brackets 1 plus 0.007 close bracket to the power of 60. So we've got 1.007 to the power of 60. 12,000 divided by that gets us a value of 7896.11. All right. That means that Suburbia Credit Union is going to allow him to spend more up front, to borrow more up front, and still be able to pay back the amount of 12,000 at the end of the day. Therefore, Lamar should choose to borrow from Suburbia Credit Union. Okay, folks, that is the end of lesson 7.3 on present value. Your practice problems for the day come from page 441. Page 441, numbers 1 through 14. Thanks for joining. Have a great day.